Hello, everyone. Thank you, Jacob, for the introduction. And thank you all for joining me today in presenting this project. So in this presentation, I will go over the motivation, the objectives of the project. I will go over a quick overview of the literature review. And then I will go over the experimental design. I will share the results of the project. And I will end with a conclusion and future work. So as the automotive industry moves toward the car of the future, companies continue to develop cutting-edge systems that aim to make driving safer, more pleasant, and more convenient. So in the future, augmented reality will play a key role in expanding the functionality of these technologies. So augmented reality, abbreviated as AR, has been developed and incorporated in the cars, and ARQs have been proven to be effective in assisting cognitive impaired elderly drivers, and they also help in directing drivers' attention to roadside hazards, and they help decrease response time for detecting hazardous objects. So as you can see in these images, these are some of the advancements in AR technologies available in today's vehicles. So we have the braking distance indicators, we have lane markings, we have vehicle detections, and we also have pedestrian detections. So pedestrians are some of the most vulnerable users of the transportation system. And augmented reality has the potential to improve the safety of vehicle and pedestrian interactions. Bad visibility of pedestrians is often the most common cause of vehicle-pedestrian accidents, along with other factors, of course. Pedestrian recognition can reduce the number of pedestrian injuries and fatalities by warning the drivers beforehand. So, the technology for pedestrian detection has already been available, and it's been used in some of the vehicles today, and various algorithms have been developed and they are successfully tested for recognizing pedestrians. These algorithms work with in-vehicle infrastructures as well as with roadside infrastructures as like vehicle and pedestrian detection systems. So in the near future, communicating the presence of pedestrians to drivers could be possible due to the advances in roadside infrastructure and for the in-vehicle technology that enables AR interfaces. So for this project, we had an objective to determine if advanced warning messages in the form of auditory and visual cues can have an impact on the detection of pedestrians bicyclists if the warning is triggered a significant distance ahead of the pedestrian or the bicyclist. And this project also had a learning and workforce development opportunity when we were creating the platform and the evaluation procedures. So in other words, what we want to do is we want to find the best interface to communicate the presence of these not visible to the driver, pedestrians or bicyclists, and we want to check like when do we need to communicate this presence to drivers. So I will go over a quick literature review. I don't want to bore you with the literature review. I want to share the results of our experiment instead. So drivers are prone to making mistakes because of human physical, perceptual, and cognitive limitations. In fact, driver error has been identified to be the main cause in approximately 93% of roadway crashes. In recent decades, humans have relied on the automobile as the primary mode of transportation. So driving has become ubiquitous and is almost second nature to most adults. However, the reality is that driving is a complex task and it requires processing large amounts of roadway and environmental information under tight time and pressure constraints. So that's why we're moving towards connected vehicles, autonomous vehicles, and these vehicles will be equipped with a variety of sensors that will be able to detect obstacles on the road. And in this case, they will be able to warn the driver before colliding. So these warning systems, they are most commonly referred to as advanced driver assistance systems, and they have been developed to enhance driving safety and driving experience. So these assistance systems, they have been highly successful in reducing the severity and the number of driving accidents. A type of these advanced driver assistance systems is the pedestrian collision warning system. And this system is used to detect the presence of pedestrians and warn the driver about the potential danger. But these systems are not well perfect, because the driver would stop immediately sometimes, and in our project we don't want the car to immediately stop. We want the driver to take action. So some manufacturers and companies such as Continental, NAVD, and others, they have already released devices and vehicles that adopt in-vehicle head-up displays, head-down displays, technology for showing, for example, navigational information, as well as other warning messages. And other manufacturers, they are now offering augmented reality solutions by overlapping graphics and text information in the real life. So that's why we're going to focus on augmented reality, as it is the new technology in these in-vehicle technologies. So the driving simulator, as you all know, it is a safer and more economical method than the on-road driving testing. And the market for in-vehicle technology continues to grow. And we have several studies that involve testing in-vehicle technology in the driving simulator. And an example of that is testing an augmented reality windshield-based in-vehicle navigation system. So I will move now towards our experiment and how we conducted our experiment and what kind of things we did. So first of all, for our project, we used our full-scale state-of-art Ford Fusion driving simulator. It's located at UW-Madison, as you can see in this picture. And the scenario that we created, it involved rural cross-sections, and they were followed by urban cross-sections. The driving was conducted in the simulator, and we emulated normal weather conditions. So it was day driving, good visibility, no rain, and we didn't include any snow. The rural portion of the driver was 2.3 miles long, and the urban portion was 2.1 miles long. So the figures on the left, they show typical rural roadway sections, cross sections for the experiment, and the figures on the right, they show the urban roadway cross sections. For the urban roadway cross sections, the speed limit was set to 25 miles per hour. So to collect subjects' responses, we added this push button, and subjects were asked to press this push button on the steering wheel once they saw a pedestrian or a bicyclist. And the responses from the push button were collected using a cell phone connected to the button via a Bluetooth connection. And timing was synchronized with our driving simulator. So here I will show you an example of the detection task. So driver would be driving from this way, and upon arrival, they are asked, they should be able to detect the bicycle, and after finishing the winding road, they should be able to detect a pedestrian. So the time at which the subjects pressed the push button was documented and expressed as a function of the simulator time. So cues about the presence of pedestrians and bicyclists were communicated to the subjects using an in-vehicle warning message and auditory signal. So as you can see on the dashboard, we created this visual warning message where it says warning ahead. It flashes for 5 seconds. I don't have the beep sound, but imagine that you're seeing this warning message and hearing the beep at the same time. So cues about the presence of pedestrians, they were communicating using using this method. So while you are driving, the time to arrival to a pedestrian is being calculated. Once this time to arrival is 20, 30, or 40 seconds, it's predetermined in the scenario we created, the audiovisual cue was triggered. And this time to arrival was calculated based on the speed of the vehicle, as we can see one more time. So here I'm gonna show you a video from inside the vehicle for what the driver experienced. As you can see, the warning message was triggered, and it means that within a specific amount of time, we will see a pedestrian, and you can see the pedestrian over here. And once the driver saw the pedestrian, they reacted to that first by clicking the push button and then with reducing their speed, stopping. It depends on how they were driving. So we can see it one more time. And here is our pedestrian. We also added these big signs to let the drivers know in which direction they should drive at intersections. So how did we split our audiovisual cues and no cues? So we had 50% of the events have no cues, and for the 50%, the other 50%, the subjects, they received visual and auditory cues for the presence of a pedestrian or bicyclist. And for these audiovisual cues, we split them into 3 different timings: the time to arrival, 20, 30, or 40 seconds. And in the next slides, I'll be referring to time to arrival of 20 seconds as Q1, time to arrival of 30 seconds as Q2, and time to arrival as 40 seconds as 15 males and 6 females. We had an average of 30 years old subjects. They were ranging from 21 to 70 years old. The oldest driver had to drop out because of simulation sickness, and we also had a technical malfunction, so we also had to drop out 1 other subject. So in total, we had 19 subjects left. So each subject encountered 7 pedestrian bicyclist events. So how did we collect this response time or response distance to pedestrians, bicyclists? So as you can see here, the driver was driving. They got this warning message. A pedestrian was crossing, and then once they saw the pedestrian or bicyclist, they clicked on the push button, and from the moment they clicked until reaching the pedestrian, that was called the reaction distance. So each driver reacted differently to seeing a pedestrian or bicyclist, and these figures show the location of the driver in X and Y coordinates along the road while approaching each of these 7 events. So we had the first 2 events were bikes on, and the rest 5 events, they were pedestrians. So for each subject, data was visually inspected to remove missing performance measures, and this is due usually to subjects not seeing an event, and they usually missed the first event. And after that, we used the median absolute deviation as a statistical filtering method. The data set was analyzed as a whole set, and the control group was compared against the 3 different Q alerts. For each group, selected summary statistics are shown in this table, so we can see the sample size for each group along with the mean and other statistical summaries. We used the nonparametric Kruskal-Wallis test instead of ANOVA because our data was not normally distributed, and the Kruskal-Wallis test works exactly the same as ANOVA. So after doing this statistical test, no statistically significant difference was found between the mean distance of groups, meaning there isn't any difference between having no Q or Q at a specific time. So for this reason, we were able, because we didn't have any statistically significant difference, we were able to group all the treatments in one group and conduct an additional analysis. So once we grouped everything into alert and no alert, we used the one-sided Wilcoxon test, which is similar to t-test, but again, because our data wasn't normally distributed, we had to go and use non-parametric tests. And this showed a statistically significant difference between the mean distances of both groups, and this distance was of 25 feet. So it means giving a Q would let drivers be aware of an event happening in front of them like 25 feet before the event. When individual speed zones were analyzed, no statistical difference was observed except for a situation in which subjects were asked to detect a pedestrian crossing the road instead of a pedestrian or bicyclist moving along the road. And the test results also indicated that the event corresponding to pedestrians crossing on a straight street, they showed a statistically significant difference between the distance means of the alert and the no alert. And subjects were able to detect the presence of the pedestrian 71 feet earlier when they had cues triggered. Now, while no statistically significant difference was observed, variances in the location where pedestrians are detected are lower when a queue is used, as you can see in this bar plot. So lower variances might suggest that when a queue is triggered, behavior is more predictable, and that could be attributed to subjects paying more attention to their surrounding and to the roadway conditions. So on average, cues were found to result in subjects detecting pedestrians sooner in terms of distance. Speed profiles were also plotted for each subject. This is an example of speed profiles. So in addition to the driver's speed, we also added the moment an alert was displayed, and this is represented in the blue dots. And every time the driver clicked on the push button when they saw a pedestrian or a bicyclist, it's also shown here with the red dots. So looking at the speed profiles for all of the 19 subjects we had, driver reduced their speed for 72% of the events after seeing an alert. And on average, they reduced their speed for 5 miles per hour. And they also reduced their speeds below the speed limit, and this gave them more time to travel. And drivers decreased their speed for an average of 14 seconds after receiving a cue. Conclusion for this project, we see that the vehicle technology has improved over time and it continues to improve. And as technology continues to evolve and connected vehicle technology becomes ubiquitous, it is conceivable that vehicle sensors will be able to detect the presence of pedestrians and bicyclists and communicate this presence to other vehicles. From this project, we saw that the distance at which pedestrians, bicyclists were detected by subjects compared to groups of events associated with cues and no cues, we saw that when a cue was triggered, statistical tests suggested that subjects detected the presence of pedestrians 25 feet earlier than when no cues were triggered. And variances in the location where pedestrians are detected were lower when cue was used. And this suggests that subjects were paying more attention to their surrounding. And when cues were triggered, for most of the events, we saw a reduction of 5 miles per hour in the speed. Now, as a future work, we had a small sample size per event. So for future work, we would like to focus on expanding the number of observations per event, and a larger sample size could help narrow the potential impact that different cue trigger times have on the detection of unexpected pedestrians and bicyclists. And the driving simulator itself has a limiting factor because of the complexity of the experiment. So as a future work, we would suggest a lower fidelity experiment to assess the spatial effectiveness of cues on the attention of subjects. And these lower fidelity experiments could be conducted using dynamic surveys that can expose participants to a pre-recorded video scenario via a computer screen. So thank you for listening to me, and if you have any questions, I'm happy to answer them.
All right, thank you, Hiba, and thank you for navigating those technical difficulties with us. We had a couple questions come in during the presentation, and we have um, a couple questions come in right now. My first question, would you be able to share the slides after this presentation? I know we will be sharing a YouTube link with the recording, but we had someone ask if the slides would be available.
Yeah, I think we can do that.
Okay, I'll touch base with you after to see what we can do there. Um, in regards to the pedestrian detection system, do you have any thoughts on how that would work in a very crowded urban area?
So so for our experiment, we didn't have anyone ahead of the driver for the urban section, but if the first vehicle would detect the presence of a pedestrian, then this vehicle would communicate that presence to the next uh, vehicle, and like maybe the first vehicle didn't need to do any reaction, and the other vehicle would need to do that. So with these infrastructure connections in the future, we see that this this is like it will help the driver to see that there's something happening in front of them, and it's up to them to see how to react.
Thank you. Um, all right, Hiba, can you explain how this work is related to augmented reality? We had that question come in at the end. I don't know if you want to expand or um, give any more details.
So augmented reality, it means adding something uh, additional. So, and in this case, our warning system inside of the vehicle is referred to augmented reality. So it can be displayed. So in our case, we displayed it on the dashboard, but it can also be displayed in different locations. So that's why it's called augmented reality.
Thank you. Okay, well, I don't see anyone else typing any questions. So think that will do it for today. Like I said, I will share this YouTube link with all of the registered attendees, so feel free to share that with any individuals that also might be interested. Um, and I will check on sharing those slides with everyone as well. So thank you for coming. We do have another webinar scheduled for February 12th. That is featuring a research project called Multimodal Distributed Simulation, combining cars, bicyclists, and pedestrians. So we hope you can make that presentation as well. Thank you, everyone, and stay warm.